Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 63. So we're still getting set to go for the next data structure of trees, and I'm still delaying them. Had some tech issues and been out of my microphone stopped working basically, so had to get a new microphone. So I think I've got it set up hopefully. This is the first real recording, but I've done several practice here adjusting settings, so hopefully I've got it sounding pretty good. So what we're going to do today, we're still not going to get the trees, but we're getting close. What we're going to look at today is references and objects. So this won't be a big lesson. In fact, I expect it'll be a little on the shorter side, but we'll make it go pretty quickly. And this is just to reinforce what we've already done, but we may not have looked at it directly. We're going to look at it a little more directly today. So in C#, there's value types and reference types. So let's do an example of a value type. So I've got my program here. So let's do this. Let's do int a equals 5, int b equals a, and b equals 10. CWA. So at this point, what we should see is here. Let's do it like this. Let's do it. We'll do it like this just so we can see both values. So here, what we will see though is this one: a equals 5, b equals 10. We'll run here without debugging. And a equals 5, b equals 10. So it works exactly like we expect. So we take a and we put it in b. So what's happening there is it copies the value of a. So if we have a type that's a class, however, things can change a little bit. So here, let's do class box public int value. All right. So now let's do this. So now we have box c equals new. Let's do it like this. Let's do new, and then we'll pass in value equals 5. So we'll do the same test here. Yeah, we'll use the newer syntax like I tried to do. And box d equals c. And now d dot value equals 10. So now cd c dot value d dot value. So now what do we think we get here? And here c and d are both 10. So what's happening in this case is that for the value types, it works as expected. Things are copied when you create them. With reference types, it's not. What happens here is the reference, the C, is copied into D. So these are referring to the same object. So then when we change the value in here in D, C also changes. So a value type stores data directly, so B has a value there. A reference type stores a pointer to the data. So the data over here is, you could think of it, it's over, let's see, let's do some text. So something like this. So we have the memory here. We have a equals 5, b equals 10, c equals, let's do it like this. Let's do we'll do 10. Let's not do that. Let's do we'll say some kind of address. I don't know. I don't necessarily care what the address is. We'll just say it's some hexadecimal value. We'll say it's a ABC. and ABC equals 5, and then C equals ABC. In some way to say it's an address, I'm just going to use an AND symbol. And then D equals, so when we assign D equals C, what we actually get is something like that. So that means these two are pointing to here. So when we change the value here, the value becomes 10. And now when we try to read it from C, the value is 10. These two are still the same. And this is a very rough example, but there's sort of conceptually what you can think is happening. So that'll be really important to keep in mind for upcoming changes. So what happens here if we say value equals null? The compiler is going to complain saying we can't do that because it's non-nullable. Oh, can we not do that? Let's do it like this. Let's make D null. There. And here it's going to complain that it's converting a null to a non-null. And I'm going to say, okay, we don't care for this case. So now what's going to happen? Now we'll get a null reference exception when we run system.null reference exception. And notice it was a runtime error, not a compile time. The exclamation point tells us it's not a problem, but the compiler here thinks it probably is a problem, but it's not 100% sure on that. And it is a problem, so it's a runtime error because it happened not when it compiled, but instead when it ran here. And what that's saying is we're trying to access something here, and it's just null. There's null, so we replaced this with null. And then we say get the value from the address here, and the address here is null, and that's invalid. And that's what's happening in that situation. So when you're passing around a lot of references, as we're going to figure out what we'll be doing with trees here very soon, a lot of times it'll you might run into this, and that's something to keep in mind. If we wanted to make this nullable here, we could do that, and that also gets rid of the compiler error. However, if we do this, we should still see the runtime error. And we do. If we add a question mark here, however, now it's addressed, and it just prints out nothing. In that case, the nothing is the null. There's nothing to actually print there, so we'll go back. Let's go back here. D.value equals 10. Back to our original example now. So let's make another class. So we have a box here, but let's do a class node. I think we already did this, but public int value, public node next, something like that. There, it's giving us a warning. It needs to have a value when it comes out of constructor. We're going to ignore that warning, but you should address that probably. Let's comment this stuff out. Okay. So now let's do this. So we'll do here. Let's do constructor. I was going to do it the other way and just set values as we go, but we'll do it as a constructor actually. I guess we can just do it like this. Int value. So we can do that. Let's make this nullable. There. Now we've taken care of both concerns, and now we can just call it like node, something like first equals new and we'll pass in 1. We'll do a second now, passing in 2. So now we'll do first dot next equals second. And here we've basically made a linked list. So let's do a prediction here. Based on what we've seen before, if we do node, another equals first, and then another dot value equals 99, what do we expect will happen here? Basically what we expect is that we expect the value of first is now 99. We can check that here. We can do CW first dot value second dot value, and we will see that that's actually the case. So there we overwrote the value there. So let's write us a little helper method here to help us. So we'll do public string toString. Let's not call it toString. Let's call it get displayable value, and we'll pass in a node, starting node. All right, so now what we're going to do is we're going to have we'll do a string builder, sp equals new, return sp.toString. Okay, so now for while, let's do this. Let's do sp.append we'll do that. Now if here, let's put it into node. That way we're not changing the starting node. Otherwise I'm about to change the starting node, and we don't want to do that. If node dot next is not null. So if it's not null, then sp.append. Let's do this. We'll do single arrow, and then node equals node.next, and then while node is not null. Continue. Okay, I think that'll do. We'll test it. CW. I need to make it static. Get displayable value, passing in first. So let's see if we got that right the first try. Not looking promising. Out of memory. Nope, not right. So let's see, what did I mess up? So do this while node is not null. Let's make that nullable actually. There. Let's add some spaces around it, but yeah, that's what I want it to do. We'll make it one arrow just to make it a little shorter. There we go. So if we added an actual third, let's add it out. Second dot next equals third. Now we should print that, and we're just passing through values like before. So if we do this, let's change this. We'll do first. Let's do node another 2 equal another second equals second. Second dot value. Your second dot next dot value equals 42. And here we'll need to do that. We need to do that. Yeah, okay. Oh, and it needs to be another second. Yeah, there we go. Okay. So now we should see that the third gets rewritten, and it does. So all that's showing how reference types you can change them and sometimes not be expecting what you're changing. So what if instead here for a second, what if instead we said let's do this equals null. Now what happens? So let's see what happens now. Everything worked. So what happened? So here we set the reference. So we set a back in the example. We set second to the value here, or another second to second, but then we just set another value to null, another second to null. So what happened there is we set an address, but then we wiped the address. We didn't change the value, so it still worked. If we wanted it not to work, we could do this. We could do this dot next equals null. And in this case, now 3 shouldn't appear in our print, and it doesn't. So that's pretty much a brief introduction here to messing around with the references a little bit. So an example of this is for like a file system, for example. Say we have our folder structure. So we have a folder, and then it has another folder inside, and then maybe a file on down inside. That's sort of like a linked list, but we'll see that you can have another folder inside, so you can have 2 folders, and suddenly you start getting a structure that looks like the tree we had last time. So I don't have it open, but sort of we have a spot here, and then 2 children or 3 children or 4 children or something like that. And that's sort of what we're looking at here, is just messing around with the references, because that's what we're going to be doing with the trees. So that's one topic I'd like to cover. So the next topic I would like to cover is recursion. So here we've messed around with reference types and value types. So let's talk recursion now. All right, so let's do this. Let's write a little function here. Look static and factorial int n. I think we've done this before. So if n equals 1, return 1, else return n times factorial of n minus 1. I can't spell return. All right, so if we call this factorial 3, let's capture that to a value. We'll print the result. So let's run that and see if we get a value, and we do. We get 6. what happens? We can hide this method. So what happened there though? So let's do this. Let's print CW. We'll just do n equals. See what value we get here. Interesting. So we got 3, 2, 1. So what happens is it calls itself, and that's called recursion. So it calls it, and then it calls the upper layer, and then upper layer. So you might get a structure something like this. Let's just do a comment here. So you might end up with a structure like this, where you have, so we start with factorial of 3, and then so that means we have 3. So this one came back. So that means that we might have something like 3 times the factorial of 3 minus 1. I'm just going to do 2. I was going to do 3. We should do it. Minus 1. That breaks down into 3 times 2 times the factorial of 2 minus 1. That breaks down into 3 times 2 times 1. And we stop there because the 1 condition is a return. And that gives us their 6. So that becomes 6 if we actually do the evaluation. So that's called recursion, though, and we'll see that with trees that you're going to use recursion quite a bit. So let's do this. Let's see if we can show this a little closer. So let's do we'll do this. Let's add braces here. So I'm going to click here and do control period and add braces. CW, we will do, I will just say returning 1 here. Let's capture the value. Equals this. CW, returning result. There. Let's see if we can capture the values a little more concretely. There we go. So that, if we look here, so the first time we get down, we return a 1. Oops. Then we return a 2, because 2 times 1 is 1. Then we return a 3. So if we expand this out to a 4, we'll get a times 4 in there as well. We'll get 24 instead. And we do. Notice the entry is going opposite of the returning values. So it goes down to the lowest first and then back up the chain. So it calculates this value first because it needs that to be able to solve this one, and it goes down until it gets to 1, and then it's done. Then it goes back up and applies 2, and then back up and applies 3, and so forth. So I guess let's comment this out just a second. So this is called a base case or a guard clause, and what it's doing is it's saying this is when you stop. I've just commented that out there. So you would think what would happen. So it'll go down to 1 and then -1 or 0 and then -1 and keep going, right? Let's see what actually happens. An error. What happened? A giant error, actually. Stack Overflow. And there we got down the negative 8,002. And yeah, that's the start of the list. Then we got a giant Stack Overflow though. So what happened? So Stack Overflow says you tried to call too many things, and I actually don't know what the limit is. It must be about 8,006, I guess. And you'll see that there's probably about that many of these. Something to that effect. So what the... Oops. Go away. So what that's saying is that you've done too many calls. So there's a limit on the number of it's called stack frames you can have, and we hit that limit. If we put a breakpoint, say here, and run it in debug mode, we can see that. Or we should have been able to see that. Oh, yeah, we can't see that because we passed it. Put it here. Nope. I clicked the wrong one. If I can click the right button, there we go. All right, so one here, we're good. So we have a call stack here. So this is saying, what was the first condition? So the first condition we called from here, and it went down to here where we hit the breakpoint. If we press F5 to continue, look, it added one. And it added another, and another, and another. And now we can sort of see what's happening. And Visual Studio lets you go back and you can see here n equals 1, while here n equals 0. And you can see what steps there are. This is called a call stack. It's how it keeps track of what methods have called where and what's expected to return. And when it goes back here, back, and until it's done. So that is a stack, like the stack data structure we've looked at, and that's how it handles calling to different methods. So if we keep adding a bunch here, let's right click on this, let's set a condition. Let's do n equals stopped at negative 8,000 something, right? Let's stop at negative 8,000 just a second. So let's see what happens. Going down, going down. I should have stopped it before 8,000. While that's happening, let me do something else. Yeah, I should have stopped it before that. Yeah, what I was looking at isn't going to show anything. Here, let's do this. Let's stop. Let's change that breakpoint. So condition n equals let's say 500, negative 500. That'll be a little quicker. And look, it stopped. So now if we look through this, there's 500 of these. It's a little hard to tell that there's actually 500, but there is. Maybe even a little more than 500. You can see negative 500 is the value of n, though. That's called a conditional breakpoint, by the way. You right click over here and you can get conditions or actions, what to do at that point. And it's being cut off here. Being cut off a lot. But disable breakpoint once hit, enable only enable when the following breakpoint is hit. So when something else happens, you can tell it to give you a specific output. You can also see, like I've already showed, but you can see like other values in your before. That's just a little show there. So back here on the call stack though, as it gets bigger, you'll see that the memory was trying to climb. If we'd make it 1,000. Continue. Oh, it's not showing it good now. You can see there though it was increasing a little bit by a little bit. I was hoping it would tell me what those are so you could see them. Private bytes. So you can see the little circles in here growing. Not a ton though, still not terribly huge, but as it's going through and creating more and more of those, that eventually this gets bigger and bigger and bigger until it reaches the point that it's limited to, and that's when you get the Stack Overflow. So that's recursion, and that's the problem if you have a recursion and don't have some kind of guard clause or stop condition, something to stop your recursion. Stop this ourselves. Let's Control K, Control U. So there's a factorial. Let's do another recursion example real quick. Let's do a public static int sum int. So here, let's do this. Let's do if n equals 1. So there's our guard clause. Return 1. Else return n plus sum of n minus 1. And there's how we get to 1, so we're counting down. Let's do it the other way. Let's count up. Wait a minute, let's do it like that. Nah, I think it'd be easier to count down. So let's see if this works. So here's instead of a factorial, it's just a summation. So let's see if this works. I may have got it wrong. So var result equals sum. Let's do sum of 10, which is 55. So that's 10 plus 9 plus 8 plus 7 plus 6 plus all the way to 1. That should give us 55. And it does 55. So that just does, it's a very similar process. So something like sum 10, and then we get 10 plus sum 10 minus 1, and then 10 plus 9 plus sum of 9 minus 1, and then 10 plus 9 plus plus sum of 2 minus 1. And then we get 10 plus 9 plus plus, because 1's our ending condition. Look, it came back again. And that equals 55 when you evaluate it. So there's just another example of a recursion and using it to solve something. So the other way to do it, we could have done public static int sum with looping int. This would have got us the same value, so we would do return sum. We'll do this int sum equals 0 for int I equals 1, I less than or equal to n, I plus sum plus equals I. Here, I believe we'll see the same thing, so we'll just switch this to sum with looping. Make sure I got it right, because it's easy to get off by 1 there, but got it right. So those are equivalents, and you might say this one's simpler, and it's actually a little more performant in C# just because it's not calling a separate function. But if you're working in a language without looping, this might be your only choice. Like you may not even have a choice. And some problems just beg to be solved with recursion, but these two aren't any of them. We'll see with trees though, it just sort of makes sense to do recursion. So factorial here, let's go back to it real quick. Let's do this. So it gets really large really quickly. There's other problems as well. Let's do a factorial of 40 and see what happens. Look, all kinds of negative numbers. So it went up and up and up and then died. So what happened? So it looped back around. So in C#, if you reached max number and add on to that, it loops back around the negative numbers. And the reason for that's just how we were handling it in the binary, and it just does that. So there's problems here, and you can see it loops around multiple times because it's adding really, really large numbers there. Another problem with recursion is sometimes, even though it makes sense to solve the problem with recursion, it's not the correct answer. So public static in Fibonacci and in here. Let's make it a long. I think this one will make better sense as a long. Let's do this. If n is less than or equal to 1, return n. Return Fibonacci n minus 1 plus Fibonacci n minus 2. So what's happening there? So a Fibonacci sequence is it's the first two numbers plus added together, basically. So if you start with a sequence like this, the first two is 1, the next two is 2, 3, 5, 8, 13, and 21. And what's that? 34? Is that right? Wait a minute. Yeah, 21. 34, yes. So something like that, though. I feel like I've got the numbers off, but basically it takes the last two and adds them together, and that's what we're doing here. So let's see what happens here if we run that. So we'll do CW Fibonacci of, let's do 1, 2, 3, 6, we'll do 7. Fibonacci of 7. So the 7th Fibonacci number. 13, so 1 off. So 1, 2, 3, 4, 5, 6, 7. So it starts at the first number. But that worked. We got a 13. If we switch to 8, we'll see the same value. 21, good. 9. 34. So everything seems to be working fine. What happens if we do a larger number? Let's say 35. So the 35th Fibonacci number. Took a second, but that's a number and that's probably right. Let's say the 36th number now. Okay, there's just a number. Didn't take that long, but it seemed to be slowing down. Yeah, that definitely seems slower. Let's go up to 40. 40, definitely slower. And you'll see as you keep going, it'll get slower and slower. Right around here, some point should be where it's going to take too long to do. Yeah, there. Let's see, let's bump it up to 45 maybe. Yeah, my fans on my computer are picking up speed there. All right, 45 didn't do too long. Here, let me do this. Let me hit a CPU usage monitor. Doesn't really show anything, but I think yeah, what did I bump it up to? 48. Go away. I didn't want Windows to do that. 48 may be the point that it takes too long. But basically what's happening here is it's really hammering one of my CPUs. Yeah, and this one might be too long. There we go. So as you can see, though, it's getting longer and longer. So what's happening there? So as it does the Fibonacci, what it has to do is it has to do a lot of work here. So the first one is just 0 and then 1. Then we add those two together to get 1. But then we have to do more work. So now, what's the Fibonacci number? So here, we'll say those are the start. So fib of n minus 1 plus fib n minus 2. And then the next one becomes that, but then you have to add the Fibonacci number previously, so then you get something like here, we'll do 5, so let's say 5. So fib 5 equals fib of 5 minus 1, 5 minus 2, which those are just 4 and 3. But how do we calculate them? Well, we have to do this, so 5 equals fib of 3 plus the fib of 2, so the previous 2 before 4, plus fib of 2 plus fib of 1. You can see how that can get big pretty quick. And 1 was our cutoff point, right? So yeah. So something like that, and then we have to do one more layer. So that becomes that plus that. Does that equal anything? 1, 2, 3, 4, 5, 6. No, we're off 1. Oh, that one should have only got broken down to 1 because we're at 1. So now, there, so 1 plus 1 plus 1 plus 1 plus 1. And that's the 5, and if we did Fibonacci of 5, we get 5? We do. So the 5th Fibonacci number. And there you can see how that explodes into it goes from that all the way to 5 of them there. And as it gets bigger and bigger, it just keeps growing and growing and growing. And that shows there that it's doing a lot of repeated work. So there's ways around that. I'm not going to do it, but you can do something called memoization. So basically you just store values you've already seen. I was going to not do it. Let's do it. We'll do that real quickly. So here. We'll do this. If right, dictionary, I think we've used these before. So int, or we'll do int long memo static though, and we don't need this there. So here, so let's do this. We'll do var result equals this. So memo dot try add add in result and return result. However, we want to do it like this. So if memo contains key in, return memo in. So there we go. So let's see what happens now. So let's go back up here. So let's see if 5 still returns 5, and it does. Let's see if 38 returns a little quicker, or 48 wasn't it? 48, see if that returns a little bit quicker, and it returns almost instantly. Let's see if we do 255. That was still pretty quiet, or pretty quick. Let's do 1,000. 1,000's pretty quick. So that's a trick there. What it's doing is it's storing off the value, so it calculates the Fibonacci value of a specific one. If it's already in the list, it's done. It wants me to use something else. If it's already in the list, though, it's done, and it just returns that. Otherwise, it recalculates it, and then it has to do the whole list, but then it gets to benefit from the same thing. If it's done the previous one before, it does it. And you can use something like that to... it's called memoization. It's a dynamic programming concept. So you're basically, that is, you're taking a memo down of what you're doing. You're keeping track of what you've already done, so you don't have to do as much extra work. I'm going to click this here, and let's see what this looks like. So use try get value. So try to get that value, and if it succeeds, return it. I don't necessarily think that's any better than the contains and then just get the value, but maybe it's a little more readable, maybe. But yeah. So there's a little messing around with a recursion, and then before that we did a little bit of work with the with reference types and struct types. So this is just a little lesson in between before we start working on trees more directly. We may have one more topic I might want to hit before we hit trees, but we may just start trees next time. We'll see. But we're going to call it for there. So this has been Programming with Shadow, episode number 63. And thanks for watching, and have a wonderful rest of your day.